Go here to data, collect feature. I'm just going to make a point here, and it's going to start to collect data from these satellites that are kind of nestled above. So right now we've got a total of 7. And if we want to see what we've done so far, that's kind of what I've been doing. So I'm keeping somewhat of a straight line, which is good. The 3 parts of my thesis were to, 1, ask where are the glaciers in the Sierra. So I conducted a map-based inventory. The second part was how have the glaciers been changing and how fast. So looking at magnitude of change and rate. And so I selected 7 glaciers out of the inventory yielded about 1,600 little ice patches and glaciers, 800 of which were larger than a 100th of a square kilometer. So out of those 800, I selected 7. Lyle Glacier was one of those. The other glaciers were Kness, which is to the north of here. I counted Lyle Glacier as 2 glaciers with 2 lobes since they behave differently. Darwin Glacier, Goddard Glacier, and Kings Canyon, and then further south in Sequoia I chose Lilliput, which is a really small glacier, and the most southern named glacier in the U.S., and another unnamed glacier, which I refer to as Pickett Peak. The rate of retreat is slowing the first 50 years compared to the second 50 years. And that's kind of linked to what we were talking about before, where these glaciers are most likely retreating into smaller areas. And so they're a little bit more protected, and so it's expected that the rate of retreat would decrease. And then the third part is what I'm still working on now is why are they changing? And we know the climate's warmed. We know that precipitation's increased a little bit over the last 50 years. And so why are we still getting melt? Spatial energy balance model that will kind of help answer and get into those things like, okay, topography's altering climate in such a way that allows these features to still exist, and how sensitive are they to changes in precipitation, how sensitive are they to changes in temperature. See that little snow patch cabin off down there?
The oldest ice in the Sierra is barely 600 years old, left over from the Little Ice Age, which ended around 1850. That means between the Younger Dryas and the Little Ice Age, a period of about 11,000 years, the glaciers of the Sierra Nevada melted away completely. Coming down out of the hard dusk winds of the Panamint. My first glimpse of the Sierras was from the southeast. Their snow tops concealed behind a solid north-stretching band of late October storm. Looming in pink-gold glows of the west, of autumn's end in the mountains.
A trench right there. But here's East Pacific Rise that comes up. Whammo goes up the Gulf and doesn't appear till we get off the Mendocino Escarpment here. In between, there is a major fault in here, system really, the San Andreas. That system links the ridge crest that comes up the Gulf with a trench, and a ridge crest out here. And that is where the American plate, North American plate, has overridden these eastern limbs of the East Pacific Rise. And so now Western California is moving with this Pacific plate in an opposite direction from these eastern plates. And so that's why Western California, west of the San Andreas Fault, moving off to the northwest. Why? Because of the encroachment of North American plate over the East Pacific Rise.
The current Sierra are young mountains. Sometime between the late Eocene and the Hempelian Pliocene, they started coming up. And they're still coming up, one earthquake at a time. Between 40 and 3 million years ago, the great fault block known as the Sierra Nevada began tilting west. Eventually, the tilting raises the area enough to catch all that fabled Ice Age Pacific weather that for 2 million years works to manufacture immense valley glaciers, intent on the mass wastage of the volcanic and metamorphic overburden of the range, slowly exhuming the voluminous Sierra batholith, the subsurface magmatic intrusion, crystallized plutonic granodiorite relic of Farallon subduction. Arriving in the North American West from the car talking about mountains. Somber, fathomless piles of left materials. Layers and layers of jostled eons compiled into battered headlands of continents. Washed up from molten inner seas. The shapes, expressions of the weathering characteristics of the materials they're made from, and of how long they've been weathering. And the kind of weather they've been subject to. first big mountains were in Colorado. The good old Sawatch, the San Juans, the Sangre de Cristo, good old freeze and fall nights in the collegiates. But my first mountains were the Alleghenies, the Monroes of Pennsylvania, Fellwalking the 7th Intersupercontinental along the staccato anticlines of the Alleghenies. Mist-laden, intermontane and west, what was once peneplain, the gouged country of the plateau, uplifted in the Pennsylvanian from her epicratonic seas and their braided deltaic coasts. Growing up in the East, I always imagined the Sierra Nevada as this frightening snowbound wall, a separate province from the Rockies, thoroughly racked by Pacific storms. The highest, snowiest, sunniest range in the lower 48, taken in by the lore. The end of the line stature. When I got high, I was glad I got high. How about you? And I fucked up in school after just getting through being high. "90 million years ago, those plutons, intruding up through the dense country rock, slowly cooling, hardening, melting together. One ongoing, deeply buried body now climactically exposed, exfoliated, denuded, and carven famously, distinguishably, the great and final impasse of the North American West. Providing right conditions for this, most southerly reach of the continent's boreal forest.